We're going to move on to our second talk. Right before we do, I'd be remiss to not mention my partner in crime, Catherine Meininger. She and I were peer reviewing and running editorial with our speakers for the last few months. She fell ill. Late yesterday, was not able to make it, so I definitely wanted to give her thanks. I think many of you know Catherine from Portrait Displays. So our next speaker is Vlad Simion. Vlad's going to talk about investigating spectral rendering techniques to improve color matching in virtual production. Vlad is a color scientist at Seismic, where he specializes in the development of advanced color pipelines for virtual production, in-camera visual effects, and immersive experiences. Vlad.
Hi, thank you, guys. Today we're going to talk about spectral rendering techniques to improve color matching in virtual production. I think the first thing I should tell you guys more about is who am I? That's a really old photo of me. I graduated RIT's Mansell Color Science Lab with a degree in, thank you, with a degree in color science last year. A lot of the work that you're going to see today is actually part of my thesis research. And right now I'm a color scientist for Seismic. We work on projects in entertainment, live events, motion pictures, and we actually face a lot of these problems ourselves. And we see their results, and we were thinking of ways we can fix them. And more so, what problem are we facing? Well, really, it's this. So I know we're looking at 4 Macbeth charts. I'm going to try to elucidate them a little bit. The 2 smaller charts are actual real charts that we have on sets. We decided to use Macbeths just because a lot of you guys already know how they look like intrinsically, so it's a little better to explain. Both of those charts are lit by real lights that we had, specifically very narrow band emitting lights, and they both were lit up by white lights. And then when we tried to simulate them in our render engine, we realized that they look very, very differently. And really the question to us was why that is that if we have, 5 different lights that are all white technically, and we measure them as being white, why do they look different versus their simulations, which all the simulations look the same? Well, more practically, this is one of the images we used on a set over at NANT many, many years ago, where, we have real assets, we have real rocks lit up by real lights, and then we are having the same rocks in our render engine. And when we change illuminations in the real world and we try to adjust parameters in our render engine, they are not tracking and they're starting to drift apart from each other. And that's a real hindrance for a lot of our artists, and a lot of our DPs. When they come on set, they want to adjust lights really quickly because they want to achieve their creative vision, and they want their virtual world to kind of follow what's happening in the real world. So the blending is similar, and they realize that a lot of times it's not as simple as let's set the light in our engine to the same temperature as the light in real life. And we actually end up having to tweak it and make it match and look good through the camera. Why does this happen? Well, let's go over a little bit of some computer graphics background. So all of the backgrounds that you guys usually see in virtual production are rendered in real-time render engines like Unreal and Unity, for example. But those engines have intrinsic limitations. They work in RGB terms. And a lot of times those values are not actually measured values. They're RGB values that an artist somewhere thought that that's what that rock should look like, or that's what that car should look like. Or even if they're measured, they were measured under a very specific illuminant in a very, very specific condition. And as soon as we start changing any of those, all those parameters, the objects will not track the same. In more color science terms, we have light sources that can be either wide band or narrow band emitters. We have a reflective sample. So in our case, we are using, for this example, the orange patch on the Macbeth. And then we get a new value for it, right? In the real life, it's the actual spectrum, but in the RGB rendering engine is just in RGB terms, because those 2 light sources that we have, while in real life, they're wildly different. If you look at them in the engine, they're both 111 code values, or they're both white lights for the engine as much as it knows. So when it tries to simulate the 2 of them, the simulation is going to end up the same. But in real life, we end up with very different ones. And in the 3 Macbeths that we have, the first one is just a pure RGB rendering. So if you take the RGB value of the patch and you multiply it by the light source, you get that. In the second one, we have the wide spectrum light. So if we use the red kind of curve for the light, then you get a less saturated, more flat image, but it integrates to like kind of a similar RGB value. And maybe like a lot of people can consider this as passing, but then, if we swap it with a narrowband emitter in real life, then suddenly that RGB value should change because our patch is a lot more saturated since there's more energy distribution in there. A little bit more CG background. So all the rendering that happens in all the engines is really just an equation. I'm not going to go over this because it is a lot of terms, but what is really important to know is that this rendering equation, it happens without any units. It's really just light that gets emitted, that bounces off of a surface and then gets seen by an observer. But in all of these software, we only have this equation in terms of RGB values. But we can swap any values and we can use really any units we want. Some modern ray tracing programs actually started tracing photons throughout and give them a wavelength. Which is something what we're trying to do is, well, let's try to move away from RGB and let's solve our problems because we don't want to, well, in reality, we don't want to waste time on set to try to adjust things and make them look good when we know we could do our simulations a lot better. It turns out we're not the first people to think of spectral rendering. This is a topic that people have been thinking since the 80s. But it's never really caught traction and we haven't really seen it happen in most places yet, especially in real time. And I mean, we can speculate why. Traditionally RGB rendering looks good enough, especially in video games when you have a dragon. If the fire is slightly red or slightly blue, it's not really a problem. It's a mythical force. But I think we're finally at a point where this is not good enough, especially when we have applications that require a higher level of accuracy than we've had in the past. I really like this photo. This is from Mark Fairchild's paper in 1999, where he tried to demonstrate why RGB and full spectral rendering cannot. It has a lot of differences, and all of these cows are lit by different light, basically. It's a really good paper that kind of sets the stage for what we're about to do. One quick note on optimizations before we actually get into this. And so I talked earlier about how the rendering works in the render engine. Well, there's basically two things that we need to care about. There's the transporting. So how do we actually trace the rays through the scene and how do we do all of the math, which we already have in the equation. But there's also the storage of it. Right now, each texture that you ever see in any of the rendering engines is just a map that basically tells the engine at each pixel, this is the RGB value that texture has. Well, now we're suddenly, if we want to go to full spectrum, there's around 401 nanometers roughly in the visible spectrum. And, going from a texture that is 3 channel to a 400 channel texture is quite a lot of data that we might not be able to manage and, properly send to the GPU in real time and, move through our system. So we should probably try to reduce those 400 terms to something more usable. Well, so the next thing we tried, we looked through previous existing literature and we try to find what have people tried to do in the past to reduce spectrums to something that's still usable and give us good results, but also manage to keep on the other side in the data as small as possible. So obviously we have the RGB rendering, which everybody's been using. We're also going to throw in fully spectral in the mix just because that's the ground truth. I guess that's not a dimensionality reduction method, but it's good for us to know like what is the best that we can possibly do. Monte Carlo is a very, very popular method. There are rendering engines out there that are using VFX right now that basically assign each ray through the scene a random wavelength. And if you trace enough of them, then eventually you'll probably fill up the spectrum. The binning method basically says that instead of sampling every 1 nanometer, what if we sample every 10, every 20, every 30 nanometers? At what point can we hide all the data enough. Principal component analysis, it's a very complicated method that basically looks at all of the spectrums we have in the scene, and it tries to find the most important characteristics and only saves those. And then polynomial method that we tested, basically we can take every spectrum and we can try to apply a polynomial function to it and only save some of the coefficients. Speaking of coefficients, how do we choose how many coefficients? So obviously for RGB, we're going to use 3 coefficients. For spectral, we went down to 300 nanometers or 301 wavelengths because our devices and our lights are mainly in that area. And then for the rest of the methods, we try to optimize it so that we can reduce delta E enough and we still don't go overboard and use too many terms. And we actually found that there's some curve where eventually, even if we add a lot more terms, we don't get a lot of lower delta E in our data. And we kind of try to apply that logic even to ones that we couldn't see. And we kind of settled on the numbers in this table. And by the way, all of this data exists in the paper that will be published, and you can take more time and digest it through it. So how can we demonstrate that, like, is Spectral actually worth it and should we do it and will it actually solve our problem, or will our Macbeth still look kind of weird? Well, we should probably do a scene like the one we had in the beginning, and we should probably use our new spectral rendering engine and try to make it work and look better. So we need a scene. We decided to choose 4 grids of samples. The first one is the Macbeth, just because everybody's familiar with how it looks. But then we also decided to choose some painting samples. As on sets, you find a lot of painted materials in buildings and whatnot. We decided to choose some textiles, kind of to try to emulate characters' costumes. A big complaint we have is that characters' costumes often look really weird when they're illuminated in different conditions. And then just to add a little bit more data, we also chose some color aid papers that we found more spectrally interesting and could potentially cause problems. We also need 4 lights. So we chose 4 lights in total. 2 of them are very narrow band emitting, similar to kind of LEDs that we find on sets. And then we have 2 sets of light, or we have 1 set of lights that is kind of wide band and kind of fills all the spectrum, and it looks a little bit more natural to how you'd find light in real life. Or outdoors rather. We also decided to measure everything at 2 color temperatures, obviously T65 because that is the native white point of a lot of these color spaces, and also 3200 Kelvin as that is a very common found temperature on a lot of the sets we are on. All right. Step 1, we had to actually measure and get reflectances and see what our interactions between all of our test targets and our lights are, just to make sure that our simulations are correct. So we took a CR300 spectroradiometer, we pointed our lights at the objects, and we took measurements of every single light matter interaction. That way we also got the reflectance curves for them, so we knew at that point what our materials are if there's no light in the system, and we also knew how they responded to each light. Step 2, now that we have all of our spectrums, we can actually start running all of our simulations. So we coded a little rendering engine in Python. By no means it was real time, but it got us what we needed. And we simulated all of our test grids, and we used the digital twins of them and of their lights and tried all of our methods to see which ones. Because all of the rendering pipelines post our rendering, so everything past of us creating the image needs to be at RGB. All of the display signals need to be RGB. We ended up using ACES CG as our color space, mainly because a lot of these targets ended up outside of sRGB, and even the Macbeth chart had one color outside of the sRGB, and when you move to 3200 Kelvin, a lot of them end up in the red outside of sRGB, so we decided to move to a little bit of a bigger color space for all of our storage and all of our sending to processors and everything past that. All right. Now that we know kind of how this looked, it's time to measure them with a camera. So we went to a studio and we pointed a camera at all of our charts and all of our lights, and we measured them and we filmed them one by one. These are just composite images just to kind of see it a little bit better. And we also need to measure rendering with the camera, and that was at Rose Stage, which we are very grateful they let us use it for a while. where we filmed all of our Macbeth charts and really all of our charts in very typical virtual production methods. So we did end up doing all the color calibrations and make sure our system is kind of in a good place to reduce all the noise from the camera to the screen. And now that we've seen how our camera perceived both our renderings and our real charts, we can compare them and see if our renderings are a little bit closer than just doing pure RGB rendering. So the charts in these images, they're all the real charts that we've seen using a narrowband and a wideband emitter. And then the little squares are the rendering methods and how they thought those charts actually look in real life. And kind of what we expect for RGB in the wideband, it's close-ish, but as soon as we go to narrowband emitters, a lot of those patches lose all of the saturation that they should have in them. And in our rendering methods using this full spectral one, but even the other spectral rendering methods, they end up getting a little bit closer and you don't see as much of a difference. For people that really like to look at charts, this is the AB plots of the CIE CAM16 values. And we have the dots are basically what we filmed and the squares are what they are in real life. Or what we filmed in real life. So we're kind of like, the RGB is still kind of off, and we get a little bit closer using our methods. What I think is really important to notice here is that there isn't necessarily a specific trend that the data takes. It's not like suddenly when you use one of the type of illuminance in RGB rendering, all of the charts suddenly become more blue or more green. It's kind of all over the place. And that makes it fixing it post very, very hard because you're no longer just applying one layer to fix it in post. You have to do multiple passes, multiple layers. And that's kind of what forced us to think, well, instead of fixing it in post, what if we fix it in pre and try to fix it way before we end up even in with that problem? That plot was very small, so I think this plot is a little bit better. I will make a note that technically we have significant differences in all of these values. If we do all the proper stats routines, the differences might not be that big, but I think it's pretty clear from this plot that when it comes to RGB rendering, the delta E and the errors between what they should have been and what they ended up being in RGB rendering is kind of off. But, as you move to more spectral methods, then you can reduce that error more and more. And there is a pretty high noise floor. I mean, the lowest values, no matter what we do, are around a 2 delta E. But even so, because we're comparing these between them, we can still look at this trend and see what happens. We're also interested in seeing how the spectral methods, if we break down the spectral, all the spectral stuff into like a few terms, and then we rebuild the spectrums from those terms, how does it actually look? So we tried we tried a few methods under both our wideband and narrowband emitters, and it turns out that we actually kind of get pretty decent spectrums when it comes to wideband, but some of the methods tend to fail on narrowband, and that is probably because of the big transitions, as narrowband emitters have very big fall-offs and very quick rises, and some of the methods, like polynomials, might not be as good as describing those and preserving those details. And it turns out that this can also, we can kind of guess how the delta E will be because the trends do follow the previous spectrums that we use in our rendering engine. Well, can we rank them? Do we actually do better? Yes, but also no at the same time. Every method that we've tested in our research has advantages and disadvantages. Choosing the number of terms and variables is really, really important as it reduces the delta E, but you're trading off more storage and a lot higher speed. So you're trying to find where is the best place between your accuracy and your performance gains. We also tried very basic versions of these methods. In the last few years, there's been higher advancement into how people want to preserve spectral information. I think about a couple months ago, we had a new paper from Intel that is trying to preserve spectral information inside JPEGs. And obviously, probably some of those methods would be a lot better nowadays. And there could be a lot more optimization done once the industry kind of adopts these methods. Are there errors in our ways? Yeah, probably. Uh, the camera to the wall calibration will never be fully perfect. This is a big problem in virtual production. We still got pretty close. These charts just show basically how good our calibration was. So basically the Macbeth that we rendered out versus the Macbeth that the camera ended up filming through the display pipeline, how close it was. And the camera didn't introduce that much noise. But I know a lot of you guys know it's not a perfect human observer, so it'll have a lot of problems, and a lot of our renderings are based kind of the human observer, and that's something that can also help a lot in the future is using this method, you can substitute your observer and your render engine with a camera. You can substitute really with anything you want, and suddenly you can kind of tell how does another observer perceive all of these images. Did we achieve what we wanted? In short, yes. We reduced delta E. Our charts are simulated properly. We can freely swap lights in our engine, and they would look correct. What we really, really hope is that some very smart people in the rendering departments will look at this and say, oh, maybe now is the time for us to actually invest into spectral rendering and try to solve a lot of problems that creatives have on sets, like in XR, VR, and virtual production, and really help drive our VFX work and make our lives easier on set, but also drive like our accuracy better. Thank you for coming to my talk.
Thanks, Vlad. I got a couple questions that were delivered at the very end of the talk. If you have questions, please use the QR codes on the side of the room to enter them in. First question is the full spectral method. Why did you still show some errors for that as your ground truth?
I think there's just noise in the whole system. I mean, there's gonna be noise between when the camera actually observes the LED wall. The LED walls tend to shift over time and they tend to heat up. So there's probably error in there. The camera itself is not a human observer, so us trying to guess or us assuming that if we measure the method and then we apply the color matching functions for the human observer to derive RGB values from them is probably the wrong approach, since the camera will perceive it differently.
All right, another question, another known problem on a virtual production set, and that's when the wall panels bleed onto the talent in addition to cinema instruments. What's your thoughts regarding that mixed lighting scenario? It's not just the cinema instruments that you need to simulate in the render, but perhaps a little bit of spill as well.
Yeah, and I think the biggest advantage of us having a spectral rendering engine too, to some extent, is that now you actually can simulate all of that spill. So during previs, the GP can say, oh, I want to use these lights on this set and I want to use these LED panels, and they will see those effects happen in real time way before he gets on set and people suddenly look magenta. He will know people might look magenta and he can plan for that ahead and he can try different lights.
Very good. Have you looked at or considered other color matching functions for your RGB renderings?
We did consider them. Unfortunately, they're very hidden. None of the camera manufacturers want to tell us what their cameras actually do. But conceivably, if someone does measure them, they could definitely use them in the rendering engines, and it will make it seem like that camera is actually seeing the world. And I know that Weta uses that for their rendering engine, where they can measure the cameras and plug them in their rendering engine, and it makes it seem like the camera is actually there seeing the VFX.
And you commented on this a little bit, but obviously, spectral techniques have a computational challenge. So you did an abridged spectral technique investigation. What do you think will happen from here? Where do we go?
I think we can optimize the bridge spectral methods, and I think we can eventually get to real-time methods that actually can happen on set. I think once we get to that, we will spend a lot of time optimizing and deciding what the best balance is really between how much we optimize the methods and how much spectral data we lose versus what is the color accuracy we want.
And so as someone who's on virtual production sets all the time, do you see workflows where we will need to give the virtual art department spectral representations of key set pieces?
I think we'll introduce a little bit more time in the prep, as we suddenly need to ask the DPs, hey, can you please give us the lights a few days before so we can measure them really quickly and put in our rendering engine. So we are introducing a bit of time, but in reality, we're not, because we would have lost that time later on trying to make things look good and match them with live gamma gain and all the controls on the LED walls. So we're really saving time in the end if we, at the end. But yes, we do have a little bit more time in the beginning.
Lots of fun, not easy questions to answer. Very good. Thanks everyone. That's all the questions we have. Thank you, Vlad.
Thank you.